Here we're going to look at a nice number theory problem from Morocco that was also sent to me by a viewer. So you guys can suggest problems. I have to admit that sometimes I get really busy and I don't notice all of the suggestions, but I'm happy to get those suggestions and do them if I can. Okay, so let's look at the statement of this problem. We want to find the smallest natural number, and by natural number I mean positive integer, such that 3 to the n minus 2 to the n is a multiple of 2015. So in other words, it's divisible by 2015. Okay, so I've got some hints worked out so you guys can maybe try this problem before we look at a solution. The first hint is that 2015 has the following prime factorization. So it's 5 times 13 times 31. So whenever you're talking about divisibility, especially divisibility by a composite number, it is often helpful to look at divisibility by the component prime numbers. Then next, there's this thing called Fermat's little theorem that might help, and that says that for all integers a, such that p does not divide a, where p is a prime, we have a to the p minus 1 is congruent to 1 mod p. And the fact that I've used the notion of congruence mod p down here means that maybe we should recall what that means. So congruence modulo m, where m is any natural number, is defined as follows. So we say a is congruent to b mod m if m divides a minus b. So in other words, a minus b is a multiple of m, or a minus b is divisible by m. So our problem is equivalent to finding an n such that 3 to the n is congruent to 2 to the n mod 2015. Okay, so maybe give this problem a go with these hints and we'll come back with a solution. Okay, so hopefully those hints were helpful. Now we're ready to look at a solution. So I want to translate this problem to the following problem, which is equivalent via this notion of congruence modulo m, which was described on the last board. So we want to find the smallest natural number, i.e. positive integer n, such that we have 3 to the n is congruent to 2 to the n modulo 2015. Great. But now we can actually spread that out into a system of congruences, and that system of congruences will have to do with the prime factors of 2015. So, like I just hinted at, this is if and only if we have 3 to the n is congruent to 2 to the n modulo 5. That would be the first prime factor of 2015. And then we have 3 to the n is congruent to 2 to the n modulo 13. And then finally, 3 to the n is congruent to 2 to the n modulo 31. Great. So now let's maybe work on each of these separately. So let's maybe work mod 5 first, then we'll work mod 13, and then finally we'll work mod 31. And then we'll try to mash all of these things together. So if we work mod 5, notice that Fermat's little theorem says that 3 to the 5 minus 1, which is 3 to the 4, is going to be congruent to 1 mod 5. But then 2 to the 4 is also congruent to 1 mod 5. Again, because 2 and 3 are not multiples of 5. But what that tells us is that 2 to the 4 is congruent to 3 to the 4 mod 5. And you might say, well, maybe they could also be equal without both being congruent to 1 mod 5. And that actually happens in this case. So let's notice that we also have 2 squared is congruent to 3 squared mod 5. And so 2 squared is 4, 3 squared is 9, but 9 is congruent to 4 mod 5. But the important thing here is that 2 is one of the divisors of 4. So if we get this kind of fact happening for some number right here, then we can prove, and this is actually how we'll finish the solution off, we can prove that the only types of numbers that are smaller that could also provide this result are the divisors of this exponent. So in this case, the only numbers smaller than 4 that could provide this result would be 1 and 2, because those are the divisors of 4. And we see that, yeah, in this case, 2 works. So here we have 2 to the 2 is congruent to 3 to the 2 mod 5. Now let's go ahead and work mod 13. So again, we're going to start with Fermat's little theorem, which will say that 3 to the 12 is congruent to 1 mod 13. And 2 to the 12 is congruent to 1 mod 13. Great. So, but that tells us that 2 to the 12 is congruent to 3 to the 12 mod 13. But that's not necessarily the smallest number that allows for this congruence. We could also have solutions that are divisors of 12. So we would also need to check the following. So 2 to the, well, what are the divisors of 12? We could check 2 to the 6. Is that congruent to 3 to the 6 mod 13? And we could check 2 to the 4. Is that congruent to 3 to the 4 mod 13? So that's another divisor of 12. We could check 2 to the 3. Is that congruent to 3 to the 3 mod 13? And so on and so forth. Well, let's maybe check some of these really quickly. So notice that 2 to the 3 is 8 mod 13. So 2 to the 3 is 8 mod 13, but 3 to the 3 is 27, which is 1 mod 13. So this congruence does not hold. And then 2 squared and 3 squared, well, you can check that that congruence does not hold either. Notice 4 and 9 are not congruent mod 13, but I don't really have room to fit that in here. Then the next thing that we can do is maybe check this 2 to the 6 and this 3 to the 6. But notice 2 to the 6 and 3 to the 6, they are both equal to 2 cubed squared and 3 cubed squared. So recall that this was 8 and this was 1. But if we square 8 mod 13, we will get 64. But notice that 64 is in fact -1 mod 13. So this does not hold either. So I'll let you guys check that as well if you want to work out all of the details. But you can check this thing, and these are congruent mod 13. So 2 to the 4 is equal to 16, but 16 is 3 mod 13. And then 3 to the 4, well, that's 81, and that is also 3 mod 13. So this one is okay. So we've got a congruent solution there. So notice, if we put these two facts together at this moment, we can see that 2 to the 4 is congruent to 3 to the 4 mod 5 times 13, or mod 65. So we're actually part of the way there already. So now let's work mod 31. And so if we work mod 31, again, using Fermat's little theorem, we know that 3 to the 30, which is 31 minus 1, is going to be congruent to 1 mod 31. And then 2 to the 30 is also congruent to 1 mod 31. Great. But that tells us that 2 to the 30 is congruent to 3 to the 30 mod 31. And then what you can do after that is check that none of the other cases work. So again, I'll let you guys maybe check that none of the other cases work, and so we land at this value right here. So this allows us to form our first good guess for the smallest value of n, and we'll check that this guess works carefully. So notice we've got 2 squared is congruent to 3 squared mod 5, 2 to the 4th is congruent to 3 to the 4th mod 13, and finally 2 to the 30 is congruent to 3 to the 30 mod 31. So since raising an exponent to an exponent works multiplicatively, that gives us some motivation to take the least common multiple of these three exponents. In other words, 2, 4, and 30. The least common multiple of 2, 4, and 30 is equal to 60. So from these three boxes here, we immediately have that 2 to the 60 is congruent to 3 to the 60 mod 5, mod 13, and mod 31. That means 2 to the 60 minus 3 to the 60 is divisible by 5, 13, and 31, which means it's divisible by 2015, but that's the same thing as these being congruent modulo 2015. So we have proven this thing, which I'll box in pink over here. But what we don't know yet is that 60 is the smallest such exponent that allows us to get at this solution. So I'll go ahead and clean up the board, and then we will show that 60 is indeed the smallest. So on the last board, we arrived at this fact. So we've got 2 to the 60 is congruent to 3 to the 60 mod 2015. And that's actually equivalent to saying that 3 to the 60 minus 2 to the 60 is a multiple of 2015 by the definition of congruence modulo 2015. What's left to show is 60 is the smallest such exponent, which will give us this congruence, and thus give us this fact that we have this object as a multiple of 2015. Okay, so let's see how to do that. So let's go ahead and suppose m is less than 60 is the smallest such number such that 2 to the m is congruent to 3 to the m mod 2015. In other words, we want to suppose we've got a number smaller than 60 that satisfies this congruence, and furthermore take the smallest such number that satisfies this congruence. Okay, cool. Next, we're going to do something which is a pretty common trick when it comes to these number theory type problems, and that is division with remainder. So let's go ahead and divide 60 by m and get the quotient and remainder. So this is sometimes called the division algorithm. So we can write 60 as m times q plus r. And here we know that r is between 0 and m. It's allowed to be equal to 0, but it is not allowed to be equal to m. This is the remainder. Like, your remainder is always less than your divisor. Okay, so now what we want to do is insert this version of 60 into this congruence up here. So notice that's going to give us 2 to the 60, but I'm going to write that as m all to the q power times 2 to the r. Again, I just use exponent rules there to change the multiplication to repeated exponentiation and so on and so forth. And then we've got the same kind of thing happening over on the right-hand side. So here we have 3 to the m to the q times 3 to the r, and these are congruent modulo 2015. But now notice that 2 to the m and 3 to the m are congruent modulo 2015. So these two are the same number. And furthermore, neither of them are divisors of 2015, so that means you can cancel them from both sides. So that's actually pretty important, that 2 and 3 are invertible mod 2015. So that means we can cancel this whole thing and this whole thing, leaving us with 2 to the r is congruent to 3 to the r mod 2015. But let's see what we've got. We've got a number smaller than m that satisfies this exponential equation. But what that tells us is that number has to be equal to 0. I guess I should say here that this one is strictly bigger than 0. Because otherwise, we would contradict the minimality of m. So let's maybe write that down. Otherwise, the minimality of m is contradicted. Okay, well, that's actually really good news, because what that tells us is that m divides 60. So in other words, if we have a number that also satisfies this exponential congruence, we know that that number must divide 60, given that 60 already divides that exponential congruence. Okay, so I'm gonna maybe like clean up the board from here down, and now it's just the case of checking all of the divisors of 60. On the last board, we noticed that if m satisfied this congruence, then m had to be a divisor of 60. So what that tells us is that m can be equal to 1, 2, 3, 4. Let's see, 5 is a divisor of 60. Let's see what else. 12 is 10, and then 12 is a divisor of 60. And then 15, 20, and 30. So those are all divisors of 60. So we want to make sure that none of those work. So I'll do a couple of them, and then I'll leave you guys to do the other ones. I will say that there is a trick here, but I don't really want to get into it because we've used enough technical tricks here. So let's maybe go ahead and check m equals 30 first. And so I am not going to work modulo 2015. I'm going to be inspired by what I saw when I was working modulo the prime factors to guess where this goes wrong. So let's maybe recall that 2 to the 30 was congruent to 3 to the 30 modulo 31. Great. And 2 to the 2 was congruent to 3 to the 2 mod 5. But now what we can do is raise each of these to the 15th power, and that tells us that 2 to the 30 is congruent to 3 to the 30 modulo 5. So all we really need to do is check what's going on modulo the remaining prime, in other words 13. So check mod 13. In other words, we want to calculate 2 to the 30 and 3 to the 30 mod 13. And there's actually a trick for doing this. It's called the method of repeated squaring. And so what it involves is writing 30 basically in its binary representation, or as a sum of powers of 2. So notice we can write 30 as 16 plus 8. So let's see, 16 plus 8 is going to be 24, and then we're going to add 4 and then a 2. Great. So what that tells me is that I really need to calculate 2 to the 30, which is going to be the same thing as 2 to the 16 times 2 to the 8 times 2 to the 4 times 2 to the 2, and I want to compare that to 3 to the 30, which is 3 to the 16, 3 to the 8, 3 to the 4, and 3 to the 2. Okay, good. And again, we're working mod 12 in all of these. So next, I want to recall from our calculations before that 2 to the 4 and 3 to the 4 were both congruent to 1 mod 13. So what that means is that this is congruent to 1 mod 13. This is also congruent to 1 mod 13. And then notice that this is going to be 1 squared because it's 2 to the 4th squared. So this is also congruent to 1 mod 13. This is also congruent to 1 mod 13. And finally, this is congruent to 1 mod 13, and this is congruent to 1 mod 13. Again, because this is going to be like 1 to the 4th power. But now we can simplify our calculation quite a bit. So let's notice that 2 to the 30 is going to be congruent to 2 squared, which is congruent to 4 mod 13. Again, because all of these parts are congruent to 1 mod 13. But then 3 to the 30 is going to be congruent to 3 squared, which is going to be congruent to 9 mod 13. Again, because all of these parts are congruent to 1 mod 13. So what that tells us is that 2 to the 30 is not congruent to 3 to the 30 mod 13. But now putting that together with these, we see that that means that 2 to the 30 is not congruent to 3 to the 30 mod 2015. Because if it were, then you would have congruence modulo all of its primes, including 13. So what we've done is eliminated 30 from the possibilities here. And then you're just going to want to do that with all of the rest of the possibilities and see that none of them works. So I'm not going to go through that. You can go through that using the same sort of calculation. But what you'll see is that none of these are okay, which tells us that this 60 up here is in fact the smallest such exponent that allows us to finish this off. And that's a good place to stop.